Hi, my name is Victor Bailey. I'm going to be talking about frames obtained by one-sided iterations of bounded operators. My collaborator in this work is Carlos Cabrelli from the University of Buenos Aires. Also want to mention the main contributors to the area of dynamical sampling. These names that we see here: Aseka, Aldruby, Bonig, Cabrelli, Christensen, and so on. So just some background for this talk. We defined the Hardy-Hilbert space on the torus to be this particular set. It's a collection of functions in L2 of the torus, such that these integrals we see here are zero whenever this power here is negative. So these are precisely functions in L2 of the torus, such that their negative Fourier coefficients are zero. Given you have some function in the Hardy-Hilbert space, then that function can be rewritten as a power series, the way we see here, where these scalars Cn form an L2 sequence. An inner function is just some function in H2 of the torus, the Hardy-Hilbert space, such that its absolute value is 1 almost everywhere on the torus. Given some separable Hilbert space and some bounded operator defined on that space, taking it from itself to itself, we say we have an invariant subspace of that operator if that subspace is closed and it gets mapped back into itself by that particular operator. The groundbreaking theorem by Berling is the following. Every invariant subspace of the shift operator on the Hardy-Hilbert space, this operator MZ, see what it does there, just multiplies the function by the variable there. All the invariant subspaces of that operator take the form some inner function times H2 of the torus. Also, whenever you have a subspace given this way, necessarily it's going to be invariant under that operator, that shift operator. So what is this theorem saying? This theorem is saying whenever you have a subspace of the Hardy-Hilbert space that happens to get mapped back into itself by this particular operator, okay, a closed subspace that satisfies that, then necessarily every element of that space can be written in the form some fixed inner function times some element of the Hardy-Hilbert space. It's a very deep result, it'd be used heavily in this talk. Just some more background for this talk. We say that a countable collection of functions or vectors inside of a separable Hilbert space is said to be a frame if it satisfies this inequality that we see here for every f and h, where these scalars C1 and C2 are positive. What do we see is happening here? For every f and h, the L2 norm of the sequence, the L2 norm squared, the sequence of inner products of the frame vectors with any f and h must be bounded above and below in the way we see there. What do we see happening in this particular inequality? Well, this upper bound tells us that if you have a frame, then necessarily that's a Bessel sequence inside that Hilbert space. And the lower bound being satisfied, what we can glean from that immediately is that a frame must be a complete set within our Hilbert space. But something that's not immediately apparent, but that you do obtain by satisfying this frame inequality, or this frame condition, it's also called, is that if you have a frame, then necessarily every element inside of our Hilbert space can be rewritten as a series in terms of these frame vectors, where these scalars CK are forming L2 sequence. And so what we see here is that if we have a frame, then necessarily every vector inside our Hilbert space has a basis-like expansion in terms of the frame vectors. When I say basis-like, because we know that if we have a basis for our Hilbert space, then necessarily we can obtain these sort of reconstructions for any f and h. However, with a basis, the scalars, these guys CK, they're unique. And what's nice about frames is that if the frame is not a minimal frame, if the frame happens to not be a basis itself, then necessarily then it's possible for there to be multiple different ways for us to rewrite the functions as a series in terms of the frame vectors. And so that these scalars CK are not necessarily unique in that case. And that fact makes frames very useful in practice and interesting objects of study in their own right. So just continuing on, this operator here, U, is said to be the synthesis operator. What does it do? It takes us from L2 into H this way. matches from the sequence of scalars to some vector inside of our Hilbert space given this way. This series converges for every L2 sequence given we have a frame. These guys FK form a frame. This operator U star, the analysis operator, just the adjoint of the synthesis operator. It takes us from vectors in H back into L2 this way. All right. The frame operator, it's just the product of the synthesis and analysis operators in the order that we see here. It's a bounded operator. It's also invertible, it's self-adjoint and positive. And what it does is it takes vectors from H back into H this way. All right, that's the frame operator. The canonical dual frame for a given frame is just this collection of vectors that we see here. You just take the frame operator, its inverse, and apply it to each of the frame vectors. You'll have the canonical dual for that frame. What's nice about the canonical dual frame is that it itself is a frame. And if you take the frame and canonical dual frame and you write series in this form, then we have an explicit reconstruction for our functions inside the Hilbert space using those two sets of vectors, those two frames. We see here that every F and H can be given, represented this way as a series in terms of these the frame and the canonical dual. Also, this equality holds that we see here, just interchanging the roles of the frame and canonical dual in that series that we saw here. So that's what's nice about the canonical dual frame of a frame. We define a Ree sequence to be just a collection of vectors, a countable collection of vectors in your separable Hilbert space that happens to form an unconditional, bounded unconditional basis for its own span closure. If its span closure is the entire Hilbert space, then we say this is a Ree basis. So just some more background, some sampling theory background here. So typically in sampling theory, what people look to do is recover functions or reconstruct functions by taking samples or values of the function at particular points or prescribed points within that function's domain. And so as we can see here in this classical sampling theorem, if we have these numbers m and m that satisfy some inequality, and we take some function within a Paley-Wiener space that satisfies some things here, then we have that any f in this particular Paley-Wiener space can be recovered by taking these samples, these values of the function across this particular, for all these values in all these points in M, as n goes over all the integers. We see here that there's a way to recover our function given we know this information about it. We know the function's value at these, what we see here, infinitely many points as we go over all the integers. Allow n to range over all the integers. Now, of course, we need to take into account what's happening with this part of that reconstruction, the series there. But what we see here, the main idea is that in sampling theory, we need to know the function's value at some points, and as we can see here, at infinitely many points within its domain in order to be able to recover that function. And that's the typical way that sampling theory the typical kind of idea that's applied. We want to sample the function at some set number of points and hope that by doing so, there's some kind of way to recover the function across its entire domain. Well, as we saw in that particular theorem, we needed to know the function's value at infinitely many points. It may have been a countable number of points. However, it was infinitely many. And that leaves a little bit to be desired. Perhaps we're not able to sample the function that we want to recover at so many points, such a dense amount of points, perhaps. Well, in order to kind of get around this, authors Vetterli and Liu, in a paper of theirs, they found a way to reconstruct functions or vectors in a particular space that they were interested in using an insufficient spatial sampling density. Maybe insufficient in the sense that it's fewer points they sampled at than what was given in that theorem from before. So, something like that. And the way that they did that was they said, okay, perhaps we can sample at this particular set of points that's maybe not enough to recover the function using that theorem from before or some other theorem kind of like it. And what we can do is, instead of just taking a look at the function and the samples that were afforded, let's take some operator, apply it to the function, this operator that, applying it to the function hopefully, and in this particular setting, it did, gave the functions future states, future state um, in time in some sense. And by applying this operator and sampling the function at the points that it was that were afforded for us to sample at the initial state, and then sampling the evolved version of the function at those exact same points, and just repeatedly applying this operator and sampling at those same the insufficient number of points for the recovery if we just sample the original function, but sampling the evolved versions and the original function at those points, and then taking into account all of these time-space samples all together, they found a way to actually compensate for that reduced spatial sampling and recover the functions that they were interested in this way. Well, in dynamical sampling, a similar thing is done. We take a function and we kind of, we take some operator, some bounded operator, and we apply it to the function and ask ourselves, okay, is there a way to look at, this function and iterations of some operator applied to that function and see if there's some kind of way to recover the function using information in some way regarding the function in those evolved states, sampling them in some way. However, in dynamical sampling, the notion of the domain of these functions that we're trying to recover is totally dealt or done away with, as we want to see if there's a way to recover functions in an abstract Hilbert space. And so instead of sampling these functions at some points within their domain, in dynamical sampling, we look to recover the functions using samples of this form. We take the function, and we apply the operator, and then we take inner products of those functions with some vectors inside of our Hilbert space coming from some countable set that we see here, G. Okay, so if we take these inner products of our function, its evolved states under some operator, and with some vectors G inside of our Hilbert space, we ask ourselves, is there a way to recover the function using that information? Well, by the definition of the adjoint, we can move this operator over and apply it to, doing so, we'll have its adjoint being applied to these guys G on the right-hand side of the inner product, so that these samples are the exact same as the ones that we see here. These values are going to be the exact same. And this is an important observation because if we think back to that frame condition, well, if we want to be able to recover any F and H using samples of this form, well, that'll be possible if these guys here, as we take in over all these values and we take these G from this countable set, we'll be able to recover F if these guys happen to form that set of vectors here that were on the right-hand side of the inner product, if those guys happen to form a frame for our Hilbert space. So this is enough information for recovery of our functions, given these vectors happen to form a frame for our Hilbert space. And it's actually the case that any F and H can be stably reconstructed from samples of this form, if and only if, actually, these guys happen to form a frame for our Hilbert space. All right. So that's really the heart of the dynamical sampling problem. We ask ourselves, if we have some vectors inside of our Hilbert space and we have some bounded operator, we iterate that operator on these vectors, and we do that. The question is, when do this set that we have here, the set of vectors coming from iterations of this operator applied to them, when is that forming a frame for our Hilbert space? That's the heart of the problem. However, the dynamical sampling problem itself was actually solved completely. It was completely solved for the finite dimensional setting in this particular paper that we see here by the authors there. So we turn our attention to the dynamical sampling problem in infinite dimensional Hilbert spaces. And so in this setting, what do? We let H be a separable infinite dimensional Hilbert space, and given some bounded operator and some fixed vector inside our Hilbert space, the problem at hand is to find conditions, necessary and sufficient perhaps, so that a system of this form is a frame for our Hilbert space. And also, this problem covers a case where we want to ask, perhaps, what are conditions for it to be a basis? What are conditions for it to be a Bessel sequence? From that frame condition, if you recall, satisfying that upper bound is from that frame condition is what makes the system a Bessel sequence. So that the system being Bessel is, kind of like halfway there to being a frame in some sense. What are conditions for it to be complete set within our Hilbert space, a minimal set, or et cetera. Really, the question is, what are conditions necessary and sufficient, perhaps, so that the system of this form has some useful properties for us in trying to reconstruct our Hilbert space using those vectors. All right. So it turns out that of course, there's a large body of work on this subject at this point, and a lot has been done, and a lot of the results, however, that have been found actually have turned out to be, sad to say, negative results. Results that show that under certain conditions, systems of that form can never be a frame. So let's look at some of these conditions or some of these results here. It turns out that if your operator is normal, then the system that we've been considering can never be a basis. All right, and that's a paper by these authors here. What's shown is that a system of this form, given T as a normal operator, can never be both complete and minimal at the same time. So it can never be an exact sequence. And since all bases are exact sequences or sets, so all bases are exact, these guys can never be a basis then. It is the case that you can have a frame given this way with a normal operator. However, that operator itself has to be some sum of rank 1 orthogonal projections scaled by some particular scalars within the disk that satisfy some property known as being uniformly separated and some other inequality, very specific form that this operator has to take in order for it for a system like this to form a frame. But what we see here, this negative result, these guys can never be a basis, and that's something that we kind of hoped to be possible, given the dynamical sampling problem considers that as well. What are conditions for us to obtain a basis this way? What's also been shown in the literature is that if your operator is unitary, well, then a system like this can never be a frame. If your operator happens to be compact, then one of these systems can never be a frame. If your operator is hypercyclic for any vector inside of H, if the iterations of that operator on some vector forms a dense subset inside of H, then for every vector inside of H, a system like this can never be a frame. If the operator happens to be self-adjoint, well then, if we take a look at this system, it's closely related to the one we've been considering. It's just taking the system we had before and normalizing the vectors so that their norms are 1. Then a system like this normalized system can never be a frame. And it's also conjectured that this particular thing holds, the fact that if you take the operator iterated and normalized, it can never be a frame. That holds also, it's conjectured, when the operator is normal as well. So it's an open problem, actually, that, if your operator is normal, these guys here can never be a frame. It's a conjecture that that's the case, an open problem, really, still. And that's by these authors here. All right, just kind of in light of all that, and in light of all those negative results, kind of begs the question as to, what's the likelihood that even a given frame, maybe say, yeah, we know that, this collection of vectors here is a frame. Well, what's the likelihood that that frame can even look like this iterated system kind of form? It really begs the question. We just saw that, under a lot of under different conditions, some many different conditions, we see that systems of this form can't be a frame. So it really begs the question as to, is it even likely for us to find frames of this form, ever? And a great step in that direction to answering that question as to, how likely is it that this could even be possible is, is this work here by Christensen and Asanasab that shows that frames with particular properties can be given in this form, so that we can actually find these sort of frames. It is possible. So let's talk about these results by Christensen and Asanasab, that kind of show us when it's even possible for a frame to even look like this, because we saw a moment ago that systems of this form, a lot of the time, given the operator has a particular property, some particular properties, they can't form frames, they can't form bases and things like that. However, we see here that a frame, if we know it is a frame, there are ways to show that frame can look like an iterated system of the form that we have been considering. So this theorem here by Christensen and Hasanasab tells us that if you have a frame, okay, well, that frame can be written in the form that we're interested in, if and only if that frame that you are given is a linearly independent frame. And so what this result is saying is that we can rewrite frames in this way, given the frame is linearly independent. But now what we're saying is not that it can be rewritten in this way with T a bounded operator. It's just, this result just covers the case when you can rewrite frames using some linear operator and obtaining this iterated system in this way. So, that's great. Now we know that any frame that looks like this necessarily has to be a linearly independent frame, even if the operator is bounded or not. It has to be a linearly independent frame. Another result by Christensen and Asanasab takes this a step further and kind of really shows what's needed to have this sort of representation of a frame in terms of iterations of a bounded operator on a fixed vector is the following. A frame admits this form with T being a bounded operator if and only if the kernel of the synthesis operator, this particular subspace of L2, the kernel of the synthesis operator happens to be an invariant subspace of the right shift operator on L2. That's this operator here that we see defined there. So this result is a very interesting one, and it tells us exactly when a frame can be given in this form with T a bounded operator. However, it's kind of a striking result in the fact that it's not really clear where it comes from. I mean, what we're seeing here is that a frame can be rewritten, and in this form, it can have this iterated system form with a bounded operator, if and only if this particular subspace of L2 happens to get mapped back into itself by this particular operator. It's a seemingly obscure result, and it's kind of unclear what causes this and where it comes from. However, this is a result that connects dynamical sampling to the theory of Hardy spaces, and it's one that allows us to find necessary and sufficient conditions for a system like this to be a frame where T is bounded. So here is a theorem in the same vein of dealing with representing frames in this way with a bounded operator. It's from the speaker's paper. A frame admits this form with T bounded if and only if that frame is either a Rees basis, so that it's a minimal frame, it's an exact frame, or it's linearly independent, and the kernel of the synthesis operator is generated by vectors of this form for some fixed scalar sequence such that its image under this unitary map taking us from L2 into the Hardy-Hilbert space happens to be an inner function. Okay, so that was a bit of a mouthful. So let's talk about what it's saying here. It's saying that if you have a frame admitting this form, okay, then that frame either is a minimal frame so that it's a Rees basis, And in that case, the kernel of the synthesis operator is just 0, or it's an overcomplete frame, is what this part is telling us. It's an overcomplete frame that's linearly independent, and that kernel of the synthesis operator can be given, it's generated by vectors of this form. That is to say, the span closure of vectors like this, iterations of that right shift operator on some fixed scalar sequence, happens to give you the entire space, that subspace, the kernel of the synthesis operator. So let's talk about how this comes about, because I mean it's a, I think, interesting result. It shows that frame can have this iterated system form if and only if this particular, when it's over complete frame, if and only if this particular subspace that governs or determines whether or not this representation is possible with the bounded operator is generated by vectors that look like the form that we had there for the frame itself. It's kind of interesting that we have this iterated system form for the kernel of the synthesis operator, which is the subspace that determines whether or not we can admit this iterated system form with a bounded operator for that given frame. So it's a, I think, interesting result. But to kind of just talk about the proof of this here, so perhaps we'll just talk about the one direction. So let's assume that we have a frame admitting this form with T bounded. Okay. Well, what we know is that then it's one or the other here. So we're going to assume this direction, but let's also assume that this is an overcomplete frame, so we can talk about the interesting case. So assume this and that it's overcomplete. Well, what we know is that the kernel of the synthesis operator is then going to be an invariant subspace of that right shift operator, okay, that guy S. Well, if that's the case, well, it actually turns out that under this particular map A, this guy, that invariant subspace of the right shift operator gets mapped to an invariant subspace of the shift, that multiplication operator, on the Hardy-Hilbert space. So what am I saying? I'm saying that invariant subspaces of that right shift operator, okay, on L2, they correspond to invariant subspaces of the shift on H2 of the torus by this map A. And since we know that in the case that we're dealing with, the kernel of the synthesis operator is an invariant subspace of that right shift operator, due to the fact that the frame is admitting this form with T bounded, well, we have that this guy corresponds to some invariant subspace of the shift, okay, on H2 of the torus by this map. So we know by Berling's theorem that all invariant subspaces of the shift operator in the Hardy-Hilbert space, they take the form some inner function times the Hardy-Hilbert space. Okay, well, so from what we had before, that tells us then that the kernel of the synthesis operator corresponds to some invariant subspace of this form, inner function times the Hardy-Hilbert space. Well, it's actually the case that all subspaces of this form can be rewritten in this way. They are actually cyclic invariant subspaces of the Hardy-Hilbert space, the cyclic invariant subspaces of this particular operator MZ. Okay, so that we see that we have this sort of cyclic structure for the subspace in H2 of the torus corresponding to the kernel of the synthesis operator. That's actually the case by applying the inverse of this unitary map A to this guy, which is just this. We'll see that the kernel of the synthesis operator admits the same cyclic structure as the corresponding subspace within H2 of the torus. Okay, so this theorem is an if and only if. There are two directions for this. I do want to go ahead and just move on. That hopefully gives some idea of how Berling's theorem and this theory of Hardy spaces is coming into play with these dynamical sampling problems. But let's continue on. So let's from now on drop the distinction of this guy S and the multiplication operator MZ that we talked about before, the shift operator on the Hardy-Hilbert space, so that S is actually just identified with the this operator MZ. So instead of talking about S being the shift on L2, now we're going to look at S as just being that same shift operator we talked about before. It's going to be just that guy MZ. They're the same thing now. So let's continue with that. A definition here, we say that a model space, and it's denoted like this, it's just some subspace of H2 to the torus of this particular form. It's the orthogonal complement of some shift invariant subspace of the Hardy-Hilbert space. We can denote that model space using that inner function, that theta there, because every invariant subspace, every shift invariant subspace of H2 to the torus is of the form some inner function times the Hardy-Hilbert space, so that these model spaces are really determined by whatever that inner function is. The model space is just being the orthogonal complement of those invariant subspaces. Okay, continuing on. A map like this here, this S theta, where theta is that inner function, we say this is a compression of the shift to K theta, where these things, this is the case, this P K theta is just the orthogonal projection on the K theta. This is a compression of the shift to K theta if it is like this, it's defined this way, where what's happening here? It's just the shift operator restricted to the model space. And like I said before, this is the orthogonal projection onto the model space. So what do you do with this? You just apply for any function that you're going to, any function inside the Hardy-Hilbert space that you want to apply the shift to, really that function has to first live within the model space you're dealing with. And you just apply the shift, and then whatever you get after applying the shift, you project back into that model space. And then that's just going to be the image of that function under the compression of the shift. What is a finite Blaschke product? A finite Blaschke product is an inner function. It's an inner function of this particular form, a product of finitely many terms there we see, where these values lambda j are coming from the disk, and this guy C is just some value in the torus. Let's note that the collection of finite Blaschke products, they form a proper subset of the set of all inner functions in the Hardy-Hilbert space. All right, so there's some more definitions and some lemmas here to talk about this deep result in just a moment. So here's just a definition. Given you've got these Hilbert spaces, complex separable Hilbert spaces, infinite dimensional ones, suppose you're given those, you have some bounded operator taking H to H, here this guy T, and a bounded operator taking K to K. We say that these pairs are similar, and we write this sort of congruence condition or similarity relation between this pair T with F, where this F is coming from H, and A with G, where this G is coming from K. We say that they're similar, those pairs, if there exists some topological isomorphism taking H into K, such that conjugating the operator T by that map L there, you get A, and the image of the vector in this pair here is going to be G. The image under L is going to be G by that map. Okay, here's a lemma. So that's just the definition there. So here's a lemma. This is going to be very useful for us. Assume that you have this similarity between these two pairs. Well, it turns out that this sort of iterated system that we have been talking about, given this one's a frame for the space H, well, it then implies that this one here will be a frame for our space K, and vice versa, of course. All right. So just note, for this definition, we needed the Hilbert spaces to be infinite dimensional Hilbert spaces, and we need this topological isomorphism. So it's a bijection, a bounded bijection with a bounded inverse, and it takes us from the one to the other. Okay, and so if we satisfy this definition of similarity, well then one iterated system, like we've been talking about, forms a frame if and only if the other one does in those pairs. All right, so or from those pairs. So here's another lemma. a model space, like how we defined before, just the orthogonal complement of some invariant or shift invariant subspace of the Hardy-Hilbert space, is has finite dimension, okay, if and only if the inner function defining this model space is a finite Blaskier product. So it's just saying the only time that a model space has finite dimension is when the invariant subspace used to define that model space happens to be, the inner function happens to be a finite Blaskier product. All right. Otherwise, if that inner function is not one of these, then necessarily the model space will have infinite dimension. All right. Another lemma for us, okay? This collection of vectors here, which is the same as these, happens to be a Parseval frame for the model space K theta. Let's talk about what it's saying here. This is saying that, first of all, and it's clear that this collection of vectors here, they form a Parseval frame for this model space because these vectors z to the n, as n goes from 0 to infinity, they form an orthonormal basis for the Hardy-Hilbert space. So projecting each of those vectors onto the model space K theta will give us a Parseval frame for that model space. What we want to really note here, though, is that this equality holds. The compression of the shift being iterated on this particular vector, the orthogonal projection onto K theta of the indicator function on the torus, these guys are the exact same as these coming from this projecting that those guys z to the n into the model space. So what's to note is that these two things are the same, and that then, in fact, this collection of vectors happens to form a Parseval frame for our model space, given whatever model space you're dealing with. All right. So here's a deep result here by Christensen, Asansov, and Philip. It's a very nice result, and let's take a look here. We see that a system of this form with T bounded is an overcomplete frame for our Hilbert space, our abstract Hilbert space, if and only if we have this similarity between the pair that here and this pair for some unique inner function. When we say unique, we mean unique up to constant multiple of modulus 1 that is not a finite Blaskier product. Okay, so before we kind of dig into this, let's just note that if we're saying that this inner function is not a finite Blaskier product, what does that tell us? That tells us that the model space that we're dealing with has infinite dimension. So just note that. So that's all that part is about. But what we're seeing here is we have a necessary and sufficient condition for a system like this, with T being bounded, if it's an for it to be an overcomplete frame for our Hilbert space. What do we need? We need to have the similarity between that operator that you're using, the operator that's being iterated on this function inside of our abstract Hilbert space. We need that operator to be similar to a compression of the shift to some particular model space. If that's the case, and we have the other things being satisfied in the definition of this similarity relation, well, what we see here is necessarily this guy will be an overcomplete frame for our Hilbert space, and vice versa. If these guys happen to be an overcomplete frame for our Hilbert space, then necessarily this is the case. All right, so let's talk about the proof of this. It's really a nice result and somewhat surprising, really, to see that an operator that's being defined on an abstract Hilbert space, and if it just happens to give us this system of this form for some vector forms a frame, then necessarily that operator is similar to a compression of the shift. It's a very, very interesting and deep result. And so let's talk about the proof of this a little bit. And I do want to maybe tackle this direction, assuming this, and then saying and concluding that this holds. So let's assume that we have this similarity here. Okay, well, from that limit we saw before, the similarity like this being the case with these pairs implies that if the iterated systems that we're interested in, if the one forms a frame for the space that it lives in, then the other one is going to be a frame for the space that it's in. Well, a moment ago, we saw that iterations of the compression of the shift onto this particular vector formed a Parseval frame for the model space, K theta. All right. Well, it's actually the case that that Parseval frame that it forms is an overcomplete frame. And although it is, it wasn't written in the previous slide, it's actually the case as well that with that lemma, the similarity, not only is it that if the one forms a frame, then the other forms a frame for its space, it's actually the case that if one is an overcomplete frame, then the other will be an overcomplete frame for its particular space as well. So we saw a moment ago that it was a lemma that these guys applied to this particular vector formed a Parseval frame for the model space that it's defined on. Well, it's actually an overcomplete frame as well, so that this particular pair is giving us an overcomplete frame. Iterating T on that particular vector is giving us an overcomplete frame for our Hilbert space. Okay, so now let's talk about the other direction. So let's assume that this system forms an overcomplete frame for H. Okay, well, assuming that T is bounded, what do we know from before? We know then that the kernel of the synthesis operator is going to be an invariant subspace, okay? And if this is an overcomplete frame, it's going to be a non-trivial invariant subspace. It's going to be right shift invariant. Well, that then implies that the kernel of this particular map, which is a map that takes us from the Hardy-Hilbert space into H, the kernel of this particular map then is going to be an invariant subspace of the shift operator on the Hardy-Hilbert space. So assuming that this is bounded and an overcomplete frame gives us that this guy is non-trivial, it gives us that it's right shift invariant. And those things imply then that the kernel of this particular map, this map that takes us from the Hardy-Hilbert space into H, is going to be, the kernel of that map is going to be a shift invariant subspace of the Hardy-Hilbert space. Well, by Berling's theorem, necessarily this kernel is going to assume this particular form. Okay, by Berling's theorem, the kernel of V will be of this form, so that if we set our model space to be the orthogonal complement of that kernel, of the kernel of this map, and we define W as just the map V restricted to K theta, well, then this guy W will then be a bijection. It'll actually also be a topological isomorphism taking us from this infinite dimensional Hilbert space to this infinite dimensional Hilbert space. And the image of this particular vector is actually just going to be this, and conjugating the compression of the shift this way gives us T, so that this similarity relation is satisfied by that definition from before. Very deep result and very interesting. And really, it's something that has motivated the joint work that Carlos and I have done and are doing that we'll see here in just a moment. So from that result, we see then that, whenever we can generate an overcomplete frame using iterations of a bounded operator, and necessarily those one-sided iterations, then necessarily that operator T had to be similar to a compression of the shift, okay, on some model space. Well, it's an interesting question as to, what are, necessary and sufficient conditions for, pairs of operators applied to some vector to form a frame. That's an interesting question. And, and perhaps, to kind of start things off in the nicest case, maybe we'll want operators that commute, and we ask ourselves, if we have bounded operators that commute, what are conditions for us to have a frame of this form in our Hilbert space? And so, like I was saying a moment ago, we just saw that in order for these bounded operators iterated on some vector to form a frame, we saw that the operator in the Hilbert space had to be similar to a compression of the shift. Well, in order to find necessary and sufficient conditions for a system like this to form a frame, perhaps we need to find some kind of way to have some similarity between these operators and some shifts. Well, there's only that one shift in the one direction, in that z direction on the Hardy-Hilbert space, the H2 of the torus. So perhaps if we turn our attention to the Hardy-Hilbert space defined on the torus squared, where there are actually two shift operators available, perhaps there's a way to obtain some similarity between the first operator that's used, the T1 that's used to generate the frame, and T2, similarity between that and the other shift that's on this particular Hardy space. And perhaps we'll be able to find necessary and sufficient conditions like the one that we saw before for a system like this to be a frame. So this is really the starting point for this, is to kind of look at this particular space and ask ourselves, is there a way we can kind of do something similar using these two different shifts that are available here in this particular space. So we define the Hardy-Hilbert space on the torus squared to just be this set of functions that are coming from L2 of the torus squared that satisfy something similar, similar to what we saw a moment ago. These particular integrals are zero if m or n is zero, okay? Where this measure is just Lebesgue measure normalized, okay? Here, if we have some function in h to the torus squared, then necessarily we still have these sort of power series-like representations of the functions, and these scalars here, they form an L2 sequence still. And a subspace is said to be shift invariant in this particular Hardy-Hilbert space on the torus squared, if it's invariant under both shift operators S1 and S2, okay? That is to say that S1 on that subspace which is going to give us Z times that space, gets mapped back into itself, and S2 on that space, which is just the shift in the W direction, it gets mapped back into M, okay? So a subspace is shift invariant in this setting if it's invariant under both multiplication by Z and multiplication by W. All right. An inner function in this particular setting is just, once again, it's a function inside of the Hardy-Hilbert space on the torus squared, such that its absolute value is 1 almost everywhere on the torus squared. All right, now what makes things kind of interesting in this new setting, and something that we have to be careful for, is this fact here that Berling's characterization of all those invariant subspaces in H2 of the torus being of the form some inner function times H2 of the torus, that characterization does not carry over fully to this particular setting. And so, it's of interest to kind of determine, what are conditions where, or to at least see from the literature, what conditions are needed so that, these invariant subspaces correspond to or take on this form in inner function times the full space, because it might be of some use to us, as we saw in the theorem from before with from Christensen, Hasanasov, and Philip. There was a mention of that inner functions when giving the necessary and sufficient conditions. In fact, it was stated that that inner function just needs to be an inner function, and it needs to not be a finite Blaschke product. Well, just doing some digging into, what happens in this particular setting, what's needed so that, you do have those subspaces taking on this particular form, that Berling type form, is something worth doing. And we'll see in a moment is actually very useful for us when finding necessary and sufficient conditions for systems of this form here to form a frame. Here's a definition for us. Given two isometries here on some Hilbert space, they're said to doubly commute on that Hilbert space if V1 commutes with V2 and V1 commutes with V2 star on H, okay? So here is a theorem, a very nice result by Mandrikar. A non-trivial invariant subspace, H2 of the torus squared. So once again, invariant means it's invariant under both S1 and S2. Well, that invariant subspace takes the form an inner function times the Hardy-Hilbert space on torus squared, if and only if those guys, S1 and S2, doubly commute on that subspace. Okay. Well, so it's of interest then to kind of talk about, well, what are some assumptions we can make on the uh, abstract Hilbert space side, on the frame for the Hilbert space side, given by these iterations of these operators, that will imply that the corresponding subspace to the kernel of the synthesis operator will have this form. That's of interest for us now if we're trying to kind of accomplish the same sort of thing that was done in the case for one operator being iterated on a fixed vector. So let's talk about this lemma here. So if we have this guy, the system generated by these two bounded operators that commute forms an overcomplete frame for our Hilbert space. All right, let's assume that and define U as the synthesis operator here on L2 there, mapping us back into H. If we define these operators, these right shift operators R1 and R2, these are operators on L2 here of this particular set. Well, let R1 be the right shift in the first component. Let R2 be the right shift in the second component for those sequences, on those sequences in this space. If R1 and R2 happen to doubly commute on the kernel of the synthesis operator, okay, if these guys do that, right, because recall that the kernel of the synthesis operator is a subset of this space, and if these two operators happen to doubly commute on this space, necessarily the invariant subspace kernel of V, which is the kernel of what we saw before with the Fourier transform first applied, then the synthesis operator applied, this subspace will then take the form an inner function times H2 of the torus squared. Okay, so here we have a condition that if we assume this regarding the frame, okay, then necessarily that subspace that we see coming into play, the kernel of this guy, that subspace we see coming into play when we define the model space and so on, we'll assume this particular Berling type form. Okay. All right. Well, so that lemma, there's a lot there. You may kind of wonder, is it really worthwhile trying to find these conditions for these invariant subspaces to take this particular form? Well, it is worthwhile, and here we'll see why. By authors Argowal, Douglas, and Clark, that it was shown in a particular paper of theirs that when you have an inner function in some invariant subspace, well, an inner function times that space gets, is contained within here, gets, the inner function times just gets mapped back into that space. So we have this here with equality if and only if that inner function here is constant. Okay, so that the only time that inner function times m is just m is when this is a constant. Otherwise, it's a proper subset where m is some invariant subspace. But something else that they showed, and that's very useful for us, is that every invariant subspace in the Hardy-Hilbert space with finite codimension, which is to say the orthogonal complement of that subspace as finite dimension, those have what's known as full range. Now, I'm not going to define what full range is exactly here. It doesn't really have any bearing on the results that we have here, but just note that whenever your invariant subspace has the property that its orthogonal complement has finite dimension, it necessarily exhibits this particular property known as being full range. Well, by Mandrikar, it was shown that invariant subspaces of this particular form, this Berling type form, they never have full range unless that inner function is a constant. So that by Berling's theorem, okay, or so not by Berling's theorem, but so that any of these Berling type subspaces, okay, we just noted by Mandrikar, these guys, they don't have full range unless the phi is a constant. So that any Berling type guy like this cannot have, they can't have finite codimension unless phi is a constant. Why? They don't have, these guys, when phi is not a constant, they can't have full range. And whenever invariant subspaces have finite codimension, they necessarily have full range. So we'll get a contradiction by assuming that the guy of this form, where phi is not a constant, has finite codimension. Okay, so because of this, these guys, they never have finite codimension unless phi is a constant. That is to say that the dimension of the space that's formed, the model space, which is formed by taking the orthogonal complement of the shift invariant subspace, whenever phi is not a constant, necessarily these guys have infinite dimension. So the orthogonal complement of one of these shift invariant subspaces of Berlin that have this Berlin type has infinite, they have infinite dimension unless this is a constant, which implies then that these guys are equal. That is to say that this is not a proper subset of h to the torus squared. Okay, so let's talk about this a little bit more. So in that theorem by Christensen, Hasanasov, and Philip, what do we see? We saw that we needed the inner function that was coming into play to not be a finite Blaschke product. And we needed that so that we could say then that the model space that we're dealing with had infinite dimension. Well, these results here tell us that in the setting of h2 to the torus squared, invariant subspaces of this form, so long as the inner function that's being used to give that invariant subspace is not a constant, then necessarily the model space in this setting, here will have infinite dimension. This is something that's needed in order to be able to apply that similarity condition, that the definition from that similarity condition. Why? Because in order to say that we had that similarity between the pairs of the operator and the vector from the Hilbert space, and then the compression of the shift in that particular vector in the Hardy-Hilbert space, in order to say that, we needed that both of the spaces, the model space and the Hilbert space, the abstract Hilbert space, had infinite dimension. So here we find a way to make sure, to guarantee that the model space that we're dealing with in this particular setting has infinite dimension. And all that's needed is for that subspace, that invariant subspace, to be of this Berlin type, with this guy not being a constant, where the inner function is not a constant. So in the other theorem from before, we saw that the inner function, what was needed was for that inner function to not be a finite Blaschke product. Well, here in this setting, all we need is if the invariant subspace looks like this, we need to make sure that this inner function is not constant. Then that model space will have infinite dimension. All right. So let's talk about this theorem here. This is by Cabrelli and the speaker. Okay, so if we just give ourselves a system of this form, where these operators T1 and T2, they're bounded and they commute, okay? And these guys, the system satisfies the property that those operators R1 and R2 happen to doubly commute on the kernel of the synthesis operator, okay? Well, this system is an overcomplete frame for our Hilbert space if and only if there exists a non-constant inner function such that this similarity holds, that congruence there, where this guy here is just the orthogonal projection onto this particular space, and this S theta 1 is just the compression of the shift to K theta of the first shift, the shift in the Z direction, and S theta 2 is the projection, or is the compression of the shift to this particular, to the same model space, compression of the shift in the W direction. Okay, so what are we seeing here? We're seeing really, we're seeing a somewhat seamless extension of the theorem from before to the case where we're talking about frames generated by orbits of, or iterations of pairs of commuting bounded operators. Why? Because we see here that we'll have an overcomplete frame for our space if and only if we find that there's some similarity between these operators here and compressions of the shifts in the Hardy-Hilbert space on the torus squared if we have a similarity between those operators and these shift operators here. So that, if this is a frame, then we have this, and that if we assume that we have this sort of similarity and this similarity between these pairs like this here, then necessarily these guys are going to be forming a frame for our Hilbert space. Now, something to note, it didn't really deliver the lemmas here regarding that are really very similar to what we saw before. But what can be shown and what has been shown in the speaker and Cabrelli's work is that these compressions of the shift, right, applied to these guys here, iterating them on this particular vector, forms a Parseval frame for that model space. And and so in the same way that we obtain that similarity, in the same way that we obtained the result from before by Christensen and Sanisab and Philip, the same sort of ideas are coming into play. These guys form a Parseval frame, and that then implies that these guys will be a frame for their space, the abstract Hilbert space, and these guys are actually going to form an overcomplete frame so that these guys do the same for the Hilbert space. That's that one direction. And then assuming this here, okay, these guys form an overcomplete frame, it also follows in a similar way that this is the case. Okay, now, a more general version of this theorem actually does hold without assuming that double commuting property of these guys, R1 and R2. And this more general theorem actually provides a characterization then of frames generated by these sort of iterations or these orbits, one-sided orbits of these commuting bounded operators. Okay, so that's a result that we had, but it's of interest to consider this case as we get to use that nice theory of these inner functions and these sort of representations of these invariant subspaces in this Berlin type form when finding this result. Okay, I want to take that. Okay, so I want to talk about some future work and current work in this area that Carlos and I are doing. So what we want to do right now is we want to kind of find out exactly when this sort of thing happens, when the system that we are generating, that T1, T2 being applied to that vector where these guys are commuting operators, we want to determine exactly when the pairs of operators satisfy that for some vector, they admit that double commuting property on the kernel of the synthesis operator. We want to see what are the operators such that for some vector you can apply that particular theorem that we saw a moment ago. Something else that we want to do, we want to perhaps apply this theory of model spaces, this Hardy-Hilbert space theory, and we want to use that to solve that open problem that I mentioned before regarding these unilateral orbits of normal operators on some vector, those normalized systems that we saw a moment ago, or a while ago, actually. But so that's that open problem. Perhaps there's a way. So what did we see before? So since I said a while ago, it may be hard to remember at this point, but it was conjectured that when T is normal, this system can never be a frame. Okay. Okay. So perhaps there's a way to apply this theory of model spaces. And why do I say that? Well, by the spectral theorem, we know that every normal operator is similar to some direct sum of these multiplication operator, or there's the same shift operators on some L2 subspace or L2 spaces. So since we're dealing with, whenever we have a normal operator, we're actually dealing with at the same time these same shift operators, these multiplication operators that we've been talking about this whole time. Now, perhaps there's a way to use this theory to determine whether or not these guys can form a frame. All right. Another thing that we want to do is we want to find necessary and sufficient conditions for systems that are given by iterations of bounded operators that nearly commute to form a frame. From what we just saw, we do have conditions that will give us, a frame using these bounded commuting operators. However, there exist systems, and Gauber frames are one example of that, Gauber systems, where the operators, they don't commute, the operators that are being iterated on the vector, they don't commute, but they nearly commute. That is to say, in particular, in the case for Gauber frames or systems, when you commute or when you interchange the order of the modulation and translation operators, which are the operators being used to generate the system, if you interchange their orders, well, they don't, you don't have equality of the other order. However, a modulus one term, a constant of modulus one, gets thrown in the mix somehow. So perhaps, and so they don't commute, but they are kind of close to commuting, those two operators for Gauber systems. So perhaps there is a way to apply the theory that we have now, for systems that are given by iterations of operators that do commute, to kind of, use that somehow to try to get us closer to tackling the case for, systems that are generated by operators that don't commute, but perhaps commute with, some constant term of modulus one thrown in the mix somehow. All right, which is the case for Gauber systems. So here are just some references, and I'd like to thank you for your time and attention.